Hello, good afternoon from Bangalore in India. My name is Partho Majumdar. We all have been using file compression or message compression, etc. for a very long time. We do compression because we want to make the size of the message of the file small so that it can be utilized in many ways, like when we are sending it across or in an email, or we are transferring it to a disk and transferring it to another machine, etc. Now, I found that we use certain compression techniques or compression tools like pkzip or some tools like this. Now, each tool uses a particular algorithm which compresses the file. Over the years, I learned that different compression techniques work best on one type of file or one type of data. It is not that every compression tool works best on all the types of data what it is provided with. So I was wondering if we could have a technique by which I could select what is the best compression technique to be applied on a certain type of data. And for doing this, I was wondering whether we could apply machine learning to take the decision as to which is the best compression technique which can be applied on a particular type of data. Now, I explain my thought through an example. What I will do is that I will explain you two compression algorithms. One I will go through in details so that even in case people are not aware of what is file compression or what is message compression, they could get a hang of that. And then I will discuss one more technique of compression in very brief, just to give a comparison between the first technique and the second technique. And then we will come to a discussion whether we really require a machine learning algorithm which can make a decision as to which is the best compression technique and then apply it on the particular text or on the particular data what it is supposed to be compressing. The compression algorithm I discuss in detail is called Huffman Algorithm. Now this is a very old algorithm. I had personally learned and programmed this way back in 1991. At that time we used C language to program this. Now suppose we have a text and this is a test text. I want to compress this. So how do we go about doing this using Huffman algorithm? Let us discuss that. The first step in Huffman algorithm is that we take all the unique characters in the text that we have to compress, and in this case I have taken out all the alphabets or the symbols, like the space is also there in this text. So I have taken out all the alphabets and symbols which is there in the text and made a list of that. Then we take the frequency of each of the symbols, that is T occurs 5 times, H occurs 1 time, I occurs 2 times, etc., and make a frequency table. So this is the first step in Huffman algorithm. After having formed the frequency table, we arrange the symbols in the descending order of their frequencies. You could do it in the ascending order also, so whichever makes it comfortable for you, you can do that. It doesn't matter to the algorithm as such. So we actually arrange the symbols in the frequencies in either the descending or ascending order. I have done it in the descending order in this illustration. Once we have the frequencies in the ascending or descending order, we start building our tree. Now to build the tree, what we have to do is that we take the frequencies which are in the lowest denomination. That is, we take where the frequency is the lowest. So in this case, you can see that we have H, A, and X, which have got the lowest frequency. We need to take two of these, so we can take any two. I take, for in this case, H and X. So after taking that, we form a node out of this by adding up the two frequencies. And here I have added the two frequencies, that is of H, that is 1, and X, that is also 1. So these two frequencies I have taken and created a node where the frequency is 2. Now, so I have one node here now. Next, we continue in the same process where I take the next two frequencies which are the lowest. So I could have taken this 2 here, and I could have taken this 1, or I also have a 2 here. So I will take this 2 and this 1 and create a node. So I do that. So here I have a node where the node's frequency is 3. So you can see it's here. Now we take the next two lowest frequencies. So you can see here I have 2 here and a 2 here. So we take these two and form a node. So we have a node where the frequency is 4. We continue this way where we take the next two lowest frequencies. You can notice that here we have a 3 and here we have a 3, So we need to make a node out of these two frequencies. So we form a node out of 3 and 3, which gives a node frequency of 6. Now we have two 4s. So one 4 is here and one 4 is here. So we form a node out of this. So I get a node frequency of 8. Next, I take the next two lowest, that is 6 and 5. So these two nodes I will take and create a node out of that where the frequency is 11. Now we have only two nodes. So we take these two nodes and form a node out of that where the frequency is 19. So you notice that this node where we have the last frequency is known as the root node. So we will call this as the root node. The frequency of the root node will be the sum of all the frequencies of all the different symbols. If you add up all the frequencies, you'll notice that it will come out to be 19. Actually, there are 19 characters in this text, so the frequency has to be 19. So now we have built the tree. Next, we will see what to do with this tree. Once we have our tree, we can make a convention that the left-hand side would be 1 and right-hand side would be 0. So I can assign a 1 on the left-hand side and a 0 on the right-hand side. I do this for all the nodes. So you can notice that I have done it for all the nodes. So I have assigned a 1 on the left-hand side and a 0 on the right-hand side. So these 1s and 0s are going to be the bits which I will assign. We will soon see how we will encode using these bits that we have assigned here. So now we come to the encoding part. Notice here that I have the symbol T. So how do I traverse to T? I go to the root node. From here, I travel left. I find a 1 here. Then I go again left from the next node and I find a 1 here. So T gets encoded as 1, 1. So the encoding for T is just 2 bits. That is 1, 1. We do it for one more. Let's take for the example S. So S, you notice that this is the path. So let's use a different color. So for S, we are doing it for S now. So I go to the root node. I find a 1 here. Then I come here. Then I find a 0 on my path. Then I go here and I find a 1 on my path. So S will be encoded as 101. So this way I will be able to encode all the characters or all the symbols that I have in my text. Notice that all the symbols have been encoded and each of them take much less than the 8 bits, what is required for normally storing the character as per the ASCII convention. So I'm using at the maximum 4 bits for some of the symbols. So I'm definitely going to be compressing the data. But is it really going to be so? Let us find out. So now I have encoded all my text. If I use this encoding, I get this pattern now. This is the pattern which I will get, which I can send across. So you notice here for the T, I have got 1, 1. So this is T. Then I have got a H. So H is 0001. So 0001, this is H. Then next is I is 001. So this is I. And then is S is 101. So this is S. 01 is space and so on. So this way I have encoded the message, and this message is going to be much less than as compared to what the original message would have looked like. Now how do we decode this? Once I receive this message, I have to be able to form this tree back for me. After I form this tree back, I start from the first bit. I say I have got a 1 here. So let's change the color once again. So I have got a 1 here. So I go to my root and I see that I have a 1. Then I go to the next character, that is next bit, that is 1 again. So I go to 1 and I notice that I have reached a leaf, and this leaf becomes T. So this 1, 1 will now become T. So I am able to decode what I have encoded. Next I go to 0. So I will come here. Again a 0. So I come here. Again a 0 and then a 1. So again I have hit a leaf. So this becomes H. So this becomes H. So I think you have got the idea how the encoding and decoding is done. So once I have encoded and decoded, let us see what is the kind of compression I get. So in the original message I had 19 characters. Each character would have taken 8 bits. So this adds up to 152 bits. My original message would have been 152 bits. Now my compressed message, if I add up, so I have got 5 number of T's, and T's will take 2 bits, so this makes 10 bits. I have got 4 spaces, and these take 2 bits, so this will make 8 bits. Like this, if I add up all the number of bits I require for my message, I notice that I require 53 bits to encode this message. So my message will take 53 bits. However, I need to store my tree, and so that I'm able to reproduce it back. So for that, I have here 8 symbols. So you can see here 1, 2, 3, 4, 5, 6, 7, 8. 8 symbols, and each symbol will take 8 bits to store, so this makes it 64 bits. And then I have to store all these symbols in my message so that I'm able to reproduce it back, and these will take 26 bits. So now if I see, my total compressed message size becomes 53 bits plus 64 bits plus 26 bits, which is actually 140 bits. 140 bits is definitely less than 152 bits, but this is not very significant. However, if you have a reasonable size text, you'll notice that the compression is very significant. In fact, theoretically, Huffman algorithm can produce compression up to 72%. So that is a huge amount of compression what you can achieve using Huffman algorithm. Now I discuss one more compression algorithm, which is known as the LZW algorithm. Now this is also a very old algorithm, and I had programmed this way back in 1991. Now in this algorithm, we look for patterns which repeat inside a text, and we create a symbol for each repeating pattern, and we replace the symbol by that repeating pattern. Now in this case, you notice this is just an example. This is not a real way of applying an LZW algorithm. It's just for the essence of giving you an idea. Like I mentioned, we are not going to discuss this in details. So now I have my text here. So this is the text. Now in this text, I notice that I have the symbols TH, and I make a symbol out of this. Now this is a ASCII text, so each of the symbols can be represented in 8 bits. So I will have between 0 to 255, which contains all the ASCII characters. So I use 8 bits to have my symbols from 0 to 255. So I can represent T using one of the symbols between 0 to 255. Then I see that I have a pattern called TH. So I could say that this TH I will represent by 256. This is 256. So 256 is a 9 bits. So using 256, I could have represented the next character, next symbol, that is TH. Then I could have taken THI and made a symbol out of this, which is going to be 257. And I could have said THIS is a symbol which will be 258, and so on. Now you notice that if I represent THIS by 258, that means I'm taking 4 bytes, that is 32 bits, and making that into a 9-bit symbol. So 32 bits gets compressed to 9 bits. Then I can see that I have this symbol IS, which is getting repeated here. So I just take IS and I make a symbol out of it. Let's say, for example, this is 267. This is not quite right, but nevertheless, this is just for illustration. So I could just replace this 2 bytes by the symbol 267. 267 also is 9 bits. So 16 bits get compressed to 9 bits. So this way we will do the compression. However, the important thing to notice here is that using this compression technique, I will achieve a compression which will be different from what we just discussed in Huffman technique. Now, for a given text, LZW will be better. For a given text, Huffman technique will be better. Which one do we choose under a given circumstance? That is the question what we have for our discussion. So we notice that we have different algorithms for compression. Each algorithm is suitable for different type of data. There are a lot of algorithms. There are different algorithms. We have just discussed 2 algorithms which are basically used for text compression, but there are algorithms which are used for image compression, etc. Now we will have these different compressions. Each algorithm is suitable for different type of data. Now which technique or which tool do we utilize for our compression, or which algorithm do we utilize for our compression? That is the question. Now to achieve the maximum mileage from our compression, we need to take the algorithm which is more suited for that particular type of data. So can we use machine learning to make a decision as to which algorithm will work best on the data what I am providing the algorithm? That is a question which I throw open to you for discussion. I am myself going to be hunting for this answer, and if I come across a mechanism to achieve this, I will publish on that. Thank you so much for listening. See you.